This is the last part of the lesson over sample means. We're going to talk about central limit theorem, which is on page 2 at the bottom, and apply it. So the rule is, for central limit theorem, if you take a large enough sample size, you know that the sampling distribution will be normal. So I'm going to write a little bit more about it. If the population is normal to begin with, then n, let's say n's size does not matter. The sampling distribution, will be normal. If the population is skewed or has an unknown shape, then n must be large to make the sampling distribution normal. The second sentence is pretty much typed right above it. The second sentence is the central limit theorem. All right, moving on. A few more things. I just talked about it, but this one's a little bit more specific. A good rule of thumb, so you have something concrete to go off of for a test, is if n is larger than or equal to 30, then normal. So let's look at this air conditioner problem. Maybe hit pause and skim through it. Something that stands out to me is this is right skewed. Population is not normal. The mean of the population is 1. Coincidentally, standard deviation is also 1. But look at this. They take a sample, so I'm going to write population stuff right there on the left, and I'm going to write sampling distribution stuff right here. N is 70. That's larger than the magic number 30 that you just saw. So we know that sampling distribution is approximately normal because n is large. You could elaborate and say because of the central limit theorem, but I don't think that's. It's important to know, be aware of the theorem, but I don't think you necessarily have to quote it right here. Let's go ahead and finish up the sampling distribution characteristics. The mean of the sampling distribution will still be 1. Standard deviation of the sampling distribution will be 1 over square root of 70, which in this case is 0.1195. All right. We haven't even addressed the question. We've just talked about the situation. This manager, this person, is going to budget 1.1 hours of work time. And the question is, will this be enough? What is the probability that the average maintenance time X bar for 70 units is going to be greater than 1.1? So we're using X bar greater than 1.1. You need to find the z-score of 1.1. Subtract the mean of the sampling distribution divided by the standard deviation of the sampling distribution, and you get 0.8368. Use normal CDF, and you get 0.2014. So this means there's a 20% chance the average time will exceed 1.1 hours. I would say most of the time that's going to be enough of a expected value, but 20% of the time it's going to exceed it. I would bump it up so that you're not surprised by the amount of time it takes to get work done. Probably should raise the budgeted time average time, I should say, to complete work. And that's it. That's the central limit theorem.